Welcome back to Bio 6612. In this lecture, we're going to talk about matrix notation and correlation structures for longitudinal data. So we reviewed this notation in the previous lecture, but I'll go over it again briefly. So when I talk about little I, that's the index for a particular subject. J is the index for a point in time, so that you have yi of j is the response value for subject I at time tij. And then x bold is a vector of covariance, where you would have x1 ij all the way up to x pij for p covariance. So I'm going to add some new notation in as well. So yij is a scalar, that's a single value. And we think of the variance of, generally, we treat the variance of any given value to be sigma squared, and that to be the same across all values. Then we also have to deal with the covariance between values in the same subject. So if you have subject I here, you have covariance between time point j and time point k for subject I. We're going to use this notation for that covariance. We also have correlation between the response for subject I at the jth and kth time point. And what is correlation? Well, correlation, which we'll also denote as rho, which is that character here, is defined for two points, x and y, as the covariance between those points divided by the square root of the variance of each of those points. And typically in longitudinal data, we'll express the variance covariance matrix in terms of the common variance and the correlation. So basically we're taking this statement here, which you can write as equal to covariance of x, y over sigma x times sigma y, because we use sigma for variance, and rearrange that to get the covariance of x and y equals sigma x, sigma y times rho. But the variances are taken to be equal for each of the time points, so you end up with sigma squared times rho. So sigma squared times the correlation at each of those time points. That's where this is coming from. So think back to linear regression for a minute. So if we take this data and perform typical linear regression, our model would be yij, we have the outcome, is equal to the x beta, the linear predictors, plus some error term. And here we actually just have a scalar value y. We'll look at this formula in matrix notation in a couple slides. So this is a vector because there might be multiple x's, and this is a vector as well because you have a beta for each x that you have. But typically with linear regression, we assume that the expectation of the error term is 0, and that the variance of the error term is sigma squared. That comes from our assumption that the errors have normal 0 sigma squared distribution. And we also assume that each error term is independent. And what that will give you is that covariance between error ij and error ik is equal to 0, which means that the correlation will also be 0. And so error ij is just the error term for subject I at time j. So it's the same, It's the same notation that we used for Yij before in the previous slide. However, when you have longitudinal data, this assumption that the errors are independent is violated because repeated measurements on a subject are likely to have correlation. So we can still assume that the expectation of the errors is 0 and that the variance is sigma squared. However, what's going to change is now we have that the covariance between error terms on the same subject, errors between measurements on the same subject are not equal to 0, which means that the correlation of those might not be equal to 0. However, we still are assuming that the subjects are independent. So sorry. And subjects being independent means that even though the covariance between errors on the same subject are not 0, you will have the covariance, let's say, between subject 1 at time point j and subject 2 at time point j. That will be equal to 0 because errors from different subjects will be independent. So sometimes it can be easier to write this in matrix notation. So I want to expose you to that notation here. And the formatting got a little bit jumbled, so I'm going to try to write it down again in a way that is hopefully a bit clearer. And we can cover this in lab as well. So take Yij to be the response for subject I at time Tij. Then bold Yi is the vector of all of the responses for subject I, and that includes the response at the first time point, second time point, all the way up until the last time point. So bold Yi is a vector of all the responses for the ith subject. And typically we have the expectation of Yij equals mu ij. The vector version of that is that the expectation of Yi equals mu I, where mu I is also a vector. So bold means vector or matrix. And not bold means you have a scalar. Then each subject will have their own variance covariance matrix that takes the form that is written out down here. But I'm also going to write it up here where you have variance of that vector yi is, so variance of a vector is going to be a matrix. Yi is going to be size ji. That's going to be a vector with a ji by 1 length because you have ji different time points. So the variance of yi is going to be a matrix of size ji by ji. And so what that matrix is going to look like is all of the diagonal entries. So your 1, 1 entry is going to be the variance of yi1. Your second diagonal entry will be the variance of yi2. All the way down to your last diagonal entry will be the variance of yiji. And then your off diagonals will be your covariances. So in the second spot, the second row of the first column, you have the covariance of between yi1 and yi2. And then covariance of yi1 and yi3 all the way up to the covariance of yi1 and yij. And this is a symmetric matrix, so everything that's in the bottom half is going to mirror what's in the top half, where this second row, first column, is going to be the covariance of yi2 and yi1, which is the same as these terms. These two terms are going to be equal. So you don't have to fill out this portion because it's equivalent to that upper portion. So every single person will have a variance matrix like this associated with each of their vector of observed time points. So then, back to linear regression, but putting this in matrix notation. The linear regression model we might be interested in would be this y equals x beta plus epsilon, where epsilon is the error. X are the covariates, betas are the weights, and y is the outcome. And in this model now, everything is either a vector or a matrix, where the y's, I'll write it out onto the side here. Y is a vector that has the stacked observations for all the subjects. Well, you might have y1, 1, y1, 2, all the way up to y1, ji, all the observations for subject 1. And then y2, 1, up to y2, ji, all the subjects' observations for subject 2, all the way up to yi, that's the last subject 1, up to yi, ji, all the observations for the last subject. So that's what that is. That's just a vector that stacks all of the observations for all of the subjects in the data set. And so this is going to be a vector of size I, big I for the total number of subjects, times the sum over all the subjects of the number of time points. That's a vector of that size. Your error term, your epsilon, is going to be a vector of the same size, stacked in the same way. Your beta is going to be a vector of beta 0, beta 1, all the way up to beta p, which is the sort of what you might be used to seeing. And your x's are going to be a matrix, where you have for the first subject, you have the first x, and then the second covariate all the way up to the pth covariate. Sorry, the x value for the first subject at the first time point for the first covariate. So you have 3 indexing spots there. And then the second row is going to be the x value for the first subject for the second time point for the first covariate for the second. And then finally, the last row is going to be the x value for the ith subject at the j ith time point for the first covariate. And so this is a matrix called your design matrix that has all your covariates. And that's going to be a matrix of size, total number of subjects with the same number of rows as your epsilon and your y. And then the number of columns is going to be p, the number of parameters that you have. So that's what this this notation means. Is it's just have a vector. It's a stack. There we go. That's expanding what each of these terms in this equation means. So linear regression for this notation assumed that your variance was sigma squared times an identity matrix. So that identity matrix just means that you have no correlation between your different epsilons. That's where that independence assumption is baked in. And for longitudinal data analysis, we assume instead that our variance is some epsilon. A variance of our epsilon is sigma squared times some matrix P, which is our correlation matrix. And we'll talk a bit more about that in the next couple slides. And so expanding on this part a little bit here. So that matrix P is itself going to be a matrix of matrices, where the first block is a matrix that describes the correlation, the covariance matrix of the first subject with everything that equal to 0 that compares one subject to a different subject. And then you're going to have a second matrix here for the second subject all the way to the last subject. So going into this a bit more, so let's just look at the notation for a single subject. And we're still using this matrix form where this is a matrix now of covariates. This is a vector of your outcome values and a vector of the error terms, the epsilon. So if we assume that variance of our epsilon, that should be a bolded one, is sigma squared pi, what are some forms that can take? So what this is asking basically is how is our data, what is the structure of how our data is correlated? And we tend to assume that, so for each subject, this is going to be a correlation matrix that has the same dimension as the number of time points. And we assume that the variance covariance matrices for different subjects are the same. So the first option is compound symmetry, which is also called exchangeable correlation structure. And this correlation structure assumes variance is constant across visits. Another way of saying that is correlation between any two visits within a subject is also constant. We'll say rho. And this approach is very parsimonious. It's easy to estimate because you only need to estimate two parameters, which you'll see in just a second in the next slide. However, it makes very strong assumptions about the structure of the correlation, and these assumptions are not usually valid for longitudinal data. So for a given subject, what this structure will look like is that the covariance of yi is equal to sigma squared, because we're assuming the same variance throughout, times this correlation matrix, which is on the diagonal term. The diagonals are the variances. So that's going to be 1 on all of the diagonals because we're multiplying by sigma squared. So It's actually sigma squared, but we've pulled sigma squared out. And then on the off diagonals are the correlations. So, and the thing about exchangeable correlation structure is that you have the same correlation at every point in the matrix. So the correlation, this is the correlation between time point 1 and time point 2, and that's going to be equal to rho. The correlation between time point 1 and time point 3 is here. That's also equal to rho. And this last one is the correlation between time point 1 and time point j, and that's also still equal to rho. So this is telling you that the correlation between two time points is the same no matter what two time points you're looking at. You always have the same correlation. Just writing out the rest of this matrix. And again, these matrices are symmetric, so what you have on the top half of the diagonal is going to match what you have on the bottom half, but I'll still write some of it out. So that's what the compound exchange or symmetry or exchangeable correlation structure looks like. And when I say it, we only have to estimate two parameters. We have sigma squared, the variance, and then rho, this correlation that's the same at each time point. So those are the two parameters that we have to estimate. So another popular covariance or correlation structure is the Toeplitz correlation structure. And this assumes variance is constant across visits, sigma squared, which we assumed in the last part, but it doesn't assume that the correlation is the same. It assumes instead that the correlation between yij and yij plus k between two different time points is different. So what that correlation structure looks like is, once again, we're going to have 1 on the diagonals, and this is always going to be the case. And then you'll have rho 1, rho 2, and here I'm saying rho is RHO, the character, which looks kind of like a P. So here we have the correlation at time point 1 and time point 2 is equal to rho 1. Then the correlation coefficient at time point 1 and time point 3 is equal to rho 2. At time point 1 and time point 4, all the way at time point j is equal to rho j minus 1, sorry, not n minus 1. And so basically at each different spacing, and then here we also have, writing out the rest of it, the correlation between, here we have the correlation between time point 2 and time point 3. That's also going to be rho 1, because what it's looking at is the difference between time points. So if you only have one spacing between time points, as you would between time point 1 and 2, or time point 2 and 3, then you get rho 1. If you have the space of 2 between time points, as you would for time point 1 and time point 3, or time point 2 and time point 4, then you get rho 2. So filling out the rest of this, you can see that the correlation between adjacent measurements is constant but you now have more parameters than we did in the previous correlation structure. In fact, you have j parameters, j being the number of time points per subject, where you have j minus 1 are related to the correlation, and then you also have sigma squared. However, there are a couple assumptions that we're making when choosing this correlation structure. One is all subjects have to have the same number of time points, and those time points are equally spaced. And they need to be equally spaced because otherwise the difference, if they're not equally spaced, then the difference between time point 1 and time point 2 might not be the same as the distance between time point 2 and time point 3. So a very popular correlation structure is the autoregressive correlation structure. And this is actually a special case of the previous structure, where you assume that the correlation between time 1 and time j and time j plus k is some exponentiated version of rho. And so let's just assume 3 time points here to make it a little bit easier to see. So what that would look like So we only have a 3 by 3 matrix because there are 3 time points. On the off diagonals, on the diagonals, you have 1 because that's the variance. At the time point 1, 2 slot, you have rho, because the difference between time points is just 1, so you could actually say that's a 1. At the 1, 3 slot, which is here, you have rho to the 3 minus 1 equals rho to the 2. And so you have rho squared. And if we were to expand this out, then, and if we had a 4 by 4, for example, the next one would be rho to the third power for 4 minus 1. So as you get time points that are farther and farther apart, this rho is going to have a higher and higher exponent value. And because rho has to be between 0 and 1, because it's a correlation coefficient, then the higher the exponent, the smaller rho is going to be. So time points that are farther apart are less correlated than time points that are closer together when you have this correlation structure. Another way of saying that is visits closer in time are more correlated. And because you're just taking different powers of rho, we still are only estimating 2 parameters here, the rho term and the sigma squared term. And this is also only suitable for measurements made at equally spaced time points. And here are a couple more types of correlation structures, though this list is not exhaustive. One is, I'm only showing you the most popular. One is called banded correlation structure, which assumes that you have one of the correlation structures you've already picked, and then at some time point out, you just say that correlation is 0 beyond that specified time point. So like maybe you think that time points after time 4 are not correlated with anything. So you just set those equal to 0 for that correlation structure. For exponential correlation, this is similar to the autoregressive structure, but instead of raising to the power of the difference in time, you actually, this is a sort of a generalization of the autoregressive pattern that you can use for unevenly spaced measurements, where the correlation decreases exponentially with the time separation between the measurements.